Hi, my name is Travis Nichols, and today we will be discussing the effect of earthquakes on structures. There are four main types of structural damage caused by earthquakes. There are ground shaking, tsunamis, fire, and ground failure, also known as soil liquefaction. Now, the scope of my study only covered ground shaking and soil liquefaction, so that's the bulk of what we'll be discussing today. Ground shaking appears to be a very obvious problem associated with earthquakes. But its effect on structures is a little bit more complicated. Now, as the ground moves, it causes the base of the building to move with it. Now, whichever direction the building moves in, or the base moves in, it appears as though the rest of the structure is moving in the opposite direction. The structure is actually not moving, only the base is. The base is moving because of inertial forces caused by ground shaking. You can't predict these inertial forces, and they can be very, very destructive. And the reason you can't predict them is because they're caused by the ground shaking. And we can't predict which way the ground moves, so we can't predict how the force is going to act. Therefore, we can't predict the cause. How can we predict the effect? Now, the resultant inertial force caused by all this movement is known as the seismic force. And that's really what you want to be designing for in a fault zone, in a seismic area. Soil liquefaction is a huge concern with earthquakes. It's mainly dependent on soil type, although some other factors such as building size can contribute a small amount. You'll find soil liquefaction in uncompacted, saturated soils, most generally fine sands. You won't find liquefaction in well-graded soils or large-grain soils. There's not enough pores, which brings me to my next point. Liquefaction is really the reduction of shear strength in the soil due to an increase in pore water pressure. So, because these finer sands have more pores to be filled by water, they're more susceptible. And then liquefaction ends up being caused by violent shaking or rapid loading, much like you see in an earthquake. And as you can see in the picture here, this is Japan just a few years ago after an earthquake, and this is the effect that liquefaction had on this apartment complex. As you can see, few of the buildings are leaning one way or the other. Then in the center we have a total structural failure, which is something that should be avoided. On the left side of this diagram, we can see this soil has a high potential for liquefaction. It's uncompacted, fine-grained, saturated soil here. You can see that all the pores there are filled with water. And on the right, as the soil begins to shake, it pulls the particles apart, leaving more pores which are still filled by the water. But because of the size of the pores, the distance between soil grains, the soil begins to move like a liquid. So you'll see a lot of landslides associated with liquefaction, just like we saw in the OSO landslide for our slope analysis project. It'll also cause structural failures like tilting. You'll see settlement issues. You'll see many, many structural failures, as we saw on the previous slide and here. So it becomes very important when you're living in a seismic area to consider the construction of earthquake-resistant structures. These structures need to deal with large forces and displacements. But going back to ground shaking, it's very hard to design for them because you can't predict how these forces are going to act. So you see here, you'll see a load distribution. With any structure, you start with a uniform distribution. But as the building moves, these loads aren't going to be uniformly distributed anymore. Okay, they're going to move unpredictably, as you can see in the figure. So instead of being in a perfectly equilibrated state, you're going from a uniform load to now you have tension, compression, and switching back and forth as the building moves, which is a very hard thing to design for. So we have to create buildings that compensate for these problems. Now there are some simple solutions here. and there are some more complicated ones. The most simple solution is really just using more ductile materials when you during the construction of these buildings. For example, concrete is very, very brittle. Therefore, it doesn't deform. It doesn't yield. So as soon as an earthquake were to hit, you wouldn't see any deformation. You wouldn't see any yield on a concrete building. It would just collapse. Whereas if you were to use steel, then you're able to get some sort of yield. You'll have some deformations. Your building might bend a little bit, but it'll stay upright. You won't have a total failure. On the left here, we have a comparison of tied foundations versus base isolation. On the right side of the figure, you have a tied foundation, which is literally tying the building to its foundation so that the building and the foundation move as one, therefore decreasing the effect of inertial forces and the seismic load. On the right, you have base isolation, which involves floating the building above its foundation on a system of bearings. Now, because of the bearings, the foundation is able to move while keeping the building relatively still. It's very, very effective, however, it's really costly. Lastly, we have active mass damping. This involves placing a large mass on top of the structure, and it's used to counteract inertial forces. So as the base of the structure is moving, the mass on top of the building is counteracting those forces acting upon the base and keeping the building still. However, this is very new technology, don't know a ton about it, and it's very expensive, so I would not recommend using that. If you're going to build an earthquake-resistant structure, if you have the funds for it, use base isolation. That is all the time that I have for this presentation. I hope you all enjoy and have a good day.